Good morning, thanks for coming. So a major theme of my PhD research is that seismicity and earthquakes that happen in ice sheets and glaciers carry a tremendous amount of information about the physical processes and about the conditions at the site at which these earthquakes happen. So in this talk, we're going to go to one of the biggest and coolest earthquakes in the world, I think. This is the Whillans Ice Plain. So as many of you know, Whillans Ice Plain is the end of the Whillans Ice Stream, which accounts for a major part of the mass flux of the Sipple Coast. It's kind of a river of fast-moving ice. And in this network here, we see it's a co-located GPS and seismic network. Really nice seismic network, records at really high frequency. And we see this really amazing process unfold where what I'm going to do is contour the area that has slipped. So it's an earthquake, and it's like an expanding crack. So it takes about 80 seconds for the rupture to propagate the 100 kilometers or so extent of the ice plain. So again, the slip is actually occurring this way, and what the contours show is this expanding circular rupture that's kind of unzipping and moving down towards the coast. If you do the multiplication, we get that this is a magnitude 7 earthquake. And in fact, it's one of the largest mass movements that's ever been recorded by seismology. It's in the top few, except it actually has a bunch of other really interesting properties also. It has a rupture velocity, so about 1.5 kilometers per second. If you are a student of rupture dynamics, this is interesting. It's right at about the shear wave speed. And it just gets better and better. These earthquakes happen twice a day. If one event is skipped, the next one's a little bit bigger. And for the rest of the talk, I'm going to go into the 30 minutes or so of sliding that happens in just one of these events. So we're going to zoom in on just one of these guys. And in the GPS data, we see this very nice velocity pulse. It has the property that it has a very quick rise time and then gradually decays, which is very consistent with our normal earthquake models, where there's rapid weakening on the interface, and then the rupture very slowly starts to feel the endpoints of the fault. It feels this slow quasi-static limitation on its overall growth. And if we look at the high frequency part of the velocity field, again, there's only one ice velocity, right? But the GPS is sensitive to the really low frequency stuff, and the seismometers are sensitive to the really high frequency part. The high frequency part, or the seismic velocity field, shows this really amazing signal. In the time domain, it looks kind of raggedy. It just oscillates around really fast. It has this envelope that decays in time. But if we look at the spectrum, things become very curious. The spectrum of this signal is characterized by these very regularly spaced spectral peaks. I've marked them there with triangles. And what's more is that these spectral peaks, they accordion. They always remain evenly spaced, but they shift to higher frequencies and have a greater spacing when the ice velocity is faster. And they shift to lower frequencies and become more closely spaced when the ice velocity is slower. So it's kind of like an accordion. Again, these are the same spectral peaks. I'm just showing the time evolution as from the previous slide. We're able to model this behavior, and specifically this is the data that I'm going to try to model, is spectrograms that look like this. We're able to model this data as quickly repeating small earthquakes. Conceptually, this is like moving a rigid, like a steel brush over a large area, and I'm picturing a big kind of a square brush that we're moving over a surface where there's a patch of gum on the surface. And the bristles, as they advance forward, some of them get stuck in the gum, and then at every kind of increment in time, when the glacier slides forward, some of them release, but then new ones get stuck. So these earthquakes, I think about them as this process of the bristles getting stuck and then releasing, stuck and then releasing, stuck and then releasing. Now we create a physics-based model of this. We simulate the evolution of earthquake friction laws, rate and state dependent friction laws for those who are savvy, and We also propagate waves away from the interface. So when there's rapid acceleration of the interface, this excites seismic waves, and we simulate the far field S waves because most of the wave field is from S waves. And when we do this, we actually come up against some pretty hard constraints about what is the physically allowable part of parameter space to make things that look like the observations. Specifically, we do a Monte Carlo inversion using Markov chains. As of this morning, I checked the results. It's still running. I've done about 100,000 simulations, and it's converging very nicely, which I was happy to see. And we come up with some unusual things, or at least for me, these were unusual based on the types of papers I usually read. So we find that the shear wave speed of the till, or whatever is down there, might be something a little bit more rigid than till, is about 1,000 meters per second. That the temperature has to be below the pressure melting point. And we think, these patches, when we figure out about how big they are, we think they're about 10 meters, and that the effective pressure is very low, about 10 kilopascals, which means, that the pore pressure has to be darn near the lithostatic or glaciostatic overburden. To place this in context, I'm used to thinking about these classic works by Richard Alley and Blankenship and these guys from the 80s, where I think about these, the shear wave speed of till as being like toothpaste or something. It's, has like 100 meter per second till wave speed. It turns out this is not a toothbrush. It's not moving over something with that low of bed rigidity. The effective pressure, similar to things that have been measured in situ, and the temperature field, the idea that the temperature is below the pressure melting point. As far as I can tell, I talked to Ian a little bit about this earlier in the meeting, and as far as I can tell, it's not inconsistent with what has been decided for the Willems ice plan to date. So I'm going to spend the rest of the talk just filling in some of these details and explain to you why I think that the bed has the properties that I just described. So there's a few things to say about this cartoon here. One is that we think that the events happen at the ice till or ice rock interface. And the reason why I think this is simply the fact that laboratory friction experiments have only ever observed the correct kind of friction that decreases as a function of velocity. This is called rate weakening friction. This has only ever been observed for this material pair and at conditions below the pressure melting point. Now, there have not been enough studies. So for example, if we want to ask the question, are the ice quakes happening entirely in the ice, or are they happening entirely in the till? Well, we can say that, I have never seen a laboratory study that reproduces the appropriate type of friction in till only. And I've never seen a study about ice sliding against ice that derives the type of parameters we need to parameterize our earthquake physics model. So other things are certainly possible, but at this point, going from the best available laboratory information, I am constrained to say that the events have to happen at the ice till interface. Another important conceptual thing about this picture is that the events are definitely happening very near, directly underneath the seismic station, and this is very closely tied to the data, which is simply that two stations that are maybe a kilometer apart, one will see the event and the other one will not, which suggests that just additional travel time from being slightly further away causes enough attenuation that the events are no longer visible. So we do think that the events are happening directly underneath the stations on which they're observed. So again, just to kind of hammer home what we think we're seeing here. So the data show on the order of 1,000 events per minute. These things are tiny and they just are popping off incredibly quickly. And when we zoom in on the data, and actually this is filtered in the range from 1 to 50 hertz, we do see this very nice repeating series of pulses that just goes on for minutes and minutes. It's a truly amazing seismic signal. And as you can see, our model captures this reasonably well. So then the question is, what about these periodic spectra? I told you that was the actual data that I'm going to model, and in my Monte Carlo simulations, that is what I do. My objective function has to do with matching the spectra. So the origin of the periodic spectra comes from the simple fact that a periodic sequence of delta functions in the time domain has the Fourier transform of a series of delta functions in the spectral domain. I'm sure that most of you could probably scratch this out on paper with a pencil in some amount of time, and it's incredibly clean analytically. It turns out we actually see it in the data also. In the bottom are the data from Willems, and the pulses have some finite width in the time domain, and as a result, the spikes in the spectral domain, they're not perfect delta functions, they have some finite width. And this then is the simple explanation for the seismograms that we have observed on Whillans. Then finally, we can explain and understand this very elegant observation that the spectral peaks change with the sliding velocity. And that explanation is simply that there are more earthquakes. The earthquakes have a shorter repeat time, and they occur more frequently at higher sliding velocities. And then, when we create physics-based models of this and try to recreate the data, we come to the conclusion that the temperature must be greater than or less than the pressure melting point, that the bed must be rigid, at least in my worldview of what the bed of Whillans usually looks like, and that there is very low effective pressure acting at the ice-till interface. Thank you.
All right. Are there questions for Brad?
That's a really important question. They reflect an area that has a length scale comparable to the fault patch, which we claim is about 10 meters. So I'm not making a claim about the 100-kilometer extent of the ice plain. That being said, we do see similar events over an aerial scale of about maybe 50 kilometers. So my mental picture is a kind of patchy bed where there are these 100-meter scale patches that exist in some region, maybe 50 kilometers in extent. But in most of the ice plain, we don't see these events. So it could be something very special about the site at which the large-scale events nucleate.